it's time to calculate pH. So we've got these three little equations up on top, and they are all in your equation packet. So none of them need to be memorized. We just got to know how to use them. Now on the surface, these equations are super easy, plug and chug. We would be given maybe something like A, the concentration of hydrogen ions. Now maybe that came from a strong acid. Maybe it was like a 0.1 molar solution of HNO3, for example, which is a strong acid. And I know that a strong acid is going to dissociate fully. So the NO3 would dissociate 100% to form hydrogen ions and nitrate ions, which I don't care about the nitrate. That guy cannot produce hydrogen and he can't take hydrogen. He's a terrible base. A good base is supposed to react with hydrogen and shift this thing in reverse. A good negative ion base is not supposed to let go of his hydrogen. And in fact, here the nitrate never reacts with the hydrogen. They always stay dissociated. So I don't care about the nitrate, but I am concerned about the hydrogen. If I'm going to calculate pH, we want the hydrogen concentration. Well, strong acids are great, because if I have a 0.1 molar solution, it's going to give me 0.1 molar hydrogen ions. And so on the surface, the calculation is a piece of cake. I would just say pH equals opposite log of 0.1 molar hydrogen ions. I'd plug it in my calculator, and out spits up 1. I say the pH is 1, game over, right? But maybe for a second we should just stop and kind of think about what this means, like blast from the algebra past. If I were to write this concentration in scientific notation, it would be 1.0 times 10 to the negative first. And now do you remember like the log log, the log base 10 is just the exponent of 10? And pH is the opposite log. So basically pH is just the opposite exponent of 10. As long as you've got a 1.0 out in front. If it would have been like 2.0 times 10 to the negative first, if the concentration would have been like 0.2, well, now you probably want to plug it in your calculator. You'll get a pH that's a decimal, and that's totally fine. And so here I would say, oh yeah, easy, the pH is a 1. Now let's say I have like 1.0 times 10 to the negative fifth molar hydrogen. Now we'd say, oh yeah, if it's a 1.0 out in front, then pH is the opposite log, which is just the opposite exponent of 10. The pH is going to be a big fat 5. Now I think sometimes people are confused on like why the higher pH numbers are for bases and the lower the pH, the more acidic the solution is. That like a pH of 1 is a more acidic solution than a pH of 5. And eventually, when we get like beyond 7, like we've been told 7 is neutral, right? And when we get beyond 7, up past like 10, 12, 14, then it's a base. Well, you got to think about that pH number and where it comes from. It's the negative exponent of 10. So yeah, like 10 to the negative first, that's a bigger number. That's more hydrogen than a concentration of 10 to the negative fifth. That's less hydrogen. So yeah, the pH 1 is more acidic. There's more hydrogen. Now, the same thing could be applied to PO8. There's something called the PO8. That's just opposite log of the hydroxide concentration. So if I had B, I could do the POH as opposite log of the OH. 1.0 times 10 to the negative third. And piece of cake, right? As long as it's a 1.0 out in front, then the opposite log is just the opposite exponent of 10. Now I'd say the POH is 3. Fantastic. All right, so I've got the pH and I've got the pOH. However, they do ask me to calculate the pH and the pOH for each of the solutions. Well, that's where that last little equation comes in handy. And again, it's super easy and it's totally in your equation packet. That if you go pH plus pOH, the sum should be 14. So in the example A, if the pH is 1, then I could just say that the pOH would be, drum roll, 13. And I could do something similar with B. If the pOH is 3, then the pH is 11. And now this kind of makes sense because often we don't use pOH a lot in the real world. We hear pH numbers all the time. I mean, if I have hydroxide, it's supposed to be a base. Well, yeah, now when I see the pH is 11, yeah, any pH over 7, the solution should be basic. Now that makes a little more sense, right? Now the other thing that I'm going to mention is that if I know the pH or the pOH, I can go backwards and tell you the concentration. So kind of like what we did in red, that if I know the pH is 1, then the hydrogen concentration must be 10 to the negative first. If the pH is 5, then the hydrogen concentration is 10 to the negative fifth. pH, the H stands for hydrogen. So if I'm looking at, let's say, example B, and I have the pH as 11, well, then the hydrogen concentration is 1.0 times 10 to the negative 11th molar. That's crazy tiny. That's super tiny. And again, I mean, pH is a measure of hydrogen in the solution. So yeah, this solution does not have much hydrogen. The hydroxide concentration is much larger. So yeah, the solution is a base. Kind of similar with example A, that if I have the pOH, I could tell you then that the hydroxide concentration is 1.0 times 10 to the negative 13. pOH gives me hydroxide concentration. Well, yeah, that's crazy tiny. Well, yeah, the hydrogen concentration is greater than the hydroxide, so the solution ends up being acidic. So eventually what we kind of do is compare. If the solution has more hydrogen than hydroxide, it should be acidic. If the concentration of hydroxide is greater than hydrogen, then the solution is a base. Pretty fantastic, right? These three equations are super easy to use. Here's one more example. The pH of blood is measured to be 7.41 at 25 degrees Celsius. And we want to calculate all of this. The pOH, the hydrogen ion concentration, and the hydroxide concentration. All right, let's do it. There's all kinds of ways that we could get this started. But if I have the pH, I could get to the pOH right away. I could use that equation pH plus pOH equals 14. Super easy, right? So I'd say 7.41 plus the pOH equals 14. And all I gotta do is subtract. 14 minus my 7.41. And I've got the pOH. It's that easy. My pOH is about 6.59. So far, so good, right? All right, now you've got a couple ways of going about the concentration of the hydrogen ion and the hydroxide ion. There's two options. So let's say option one. Option one is that we could kind of do what we were just doing and saying that if I know the pH and that number is the opposite exponent of 10, let's just go backwards. And we could say then that the hydrogen ion concentration would be based on the pH. And so I could say like 1.0 times 10 to the negative 7.41. You could do that. Just take the pH and put it up there as the opposite exponent of 10. And then this would just be like molarity. Now, while that is fine, it's kind of taboo to leave an exponent that's a decimal. So if you just plug this in your calculator, just go 10 caret negative 7.41. It'll simplify things for you. And so the answer that you'd probably see more often on like an AP exam would be something like 3.9 times 10 to the negative 8th. So this might be the preferred answer. I mean, the exponent is going to be close to 7, or I should say negative 7. It gives me a decimal out in front, but now my exponent is a whole number. You could do the same thing then with the hydroxide. You could say, all right, to get the hydroxide concentration, I got to use the POH, because that's based on the hydroxide ion, 1.0 times 10 to the negative 6.59. But then we're going to plug it in our calculator to simplify things. And so you really just say 10 caret negative 6.59. Here we go. We've got about maybe like 2.6-ish times 10 to the negative 7. And again, that might be the preferred answer. Not bad, right? Not hard. It's just using some of those little equations, and they're all in the packet. There's one other equation that's in the packet. And here's another one that you could use. So I'm going to say this is option 2. All right, so you'd have to calculate, let's say you calculated the hydrogen concentration. Or maybe you're given the hydrogen concentration and you're looking for the hydroxide concentration. There is an equation that looks like this. Hydrogen times hydroxide equals 10 to the negative 14th. It's kind of based on the equation for the dissociation of water. But this will be true of any solution. It's just that for water, it's been experimentally determined that there's always a 1-to-1 ratio of hydrogen and hydroxide, and that experimental concentration is 10 to the negative 7. 10 to the negative 7 times 10 to the negative 7 gives you 10 to the negative 14. So that's kind of a constant. Well, this will apply to any solution. It's just that if the solution is acidic, the scale is going to tilt toward the hydrogen. There's going to be more hydrogen, less hydroxide. If it's a base, then there's more hydroxide and less hydrogen. But the product of those two ions will always be 10 to the negative 14th. So let's say you knew the hydrogen concentration, or like here, maybe I already calculated the hydrogen concentration. You could just say then 3.9 times 10 to the negative 8th molar hydrogen. And then I'm going to solve for hydroxide. And I know together they're 10 to the negative 14th. So this might come in handy, like if we would have been given the hydrogen concentration, and from there they wanted me to calculate the POH or determine the hydroxide, then this little equation comes in kind of handy too. And so I just take my 10 to the negative 14th and I divide by 3.9 times 10 to the negative 8. And I get the same answer. My hydroxide ends up being about 2.6 times 10 to the negative 7th molar.